Everyone. It's my pleasure to be the chair of this session. Welcome to the speakers and the audience. Before we begin, let me introduce myself. I'm Masmoudi Marwa, a PhD student in the Faculty of Sciences of Tunis. In this session, we have 4 talks, each one of 30 minutes. The first speaker is Professor Chil from University of Tunis, Tunisia. His talk is entitled Orthogonally Additive Polynomials or Riesz spaces. Welcome, Professor. You can start.
Thank you very much. I would, in the first, I would like to thank very much the organizing committee to give me this opportunity to give my recent works and my recent research about a very important subject in the Riesz space, such the orthogonally additive polynomials in Riesz space. And we start with some definition to give the different state of this talk. A multilinear mapping T from a space product of a space E in a topological vector space F is said to be orthogonally orthosymmetric if we have Tx1, n equal to 0 whenever there are 2 disjoint elements. And we can remark about this difference that we can need the codomination to be a Riesz space. It's sufficient to be a vector lattice. And the definition of homogeneally polynomials of degree n is if we have Px is some multi-linear maps from n for f, and C is said that the multilinear operator of P. Homogeneous polynomials of degree n is said to be orthogonally additive if we have Px plus y is equal to Px plus Py if x and y are orthogonally element. And if we done by the all and homogeneous orthogonally additive polynomials by bit 0 and f. And in the first, we give some introduction about this theory of operator. One of the relevant problems in operator theory is to describe orthogonally additive polynomials via linear operator. This problem can be treated in different manner depending on domain and codomain on which polynomials acts. Interesting in orthogonally additive polynomials on Banach space originated in the work of Sanderson, where the space of n homogeneally orthogonally additive polynomials on Banach space, capital LP and minimal LP, was characterized. It is only recently that the class of such mapping have been getting more attention. We are thinking here about some works in the case of the different Banach lattice and C-star algebra. Proofs of the aforementioned result are strongly based on the representation of this space of these spaces as vector subspaces of extended continuous functional by the Kitatini theorem representation. So they are not applicable to general case of Riesz spaces. That is why we need to develop new approach. Actually, the innovation of this work consisting in making a relationship between mapping, which leads to a and this manner leads to a constructive proof of Sanderson results. And then we give some historical about this subject. The interesting in orthogonally additive polynomials on Banach lattices originate in the work of Sanderson in capital LP and minimal LP, in which he characterized the orthogonally additive polynomials by integral representation. After that, some authors like Garza, Villanova, and Carrando, Lazal, and they characterized the polynomial, the additive polynomials in the case of C of x space by a representation integral and by some measure, Borel measure, me. And after that, there are some works in the case of Banach-Lattice by Binyami, Lazel, and Yonov. In the case of Binyami, in the case of Banach-Lattice, in the general case of Banach-Lattice. By using heavily the representative space as vector space of extended functional continuous, some authors have proven a resultantist analogies to Sanderson for the class of Banach-Lattices of functional of order continuous functional space, who deals is given by show the analogous resultants. And after that, for example, in the case of C12 algebra and in holomorphic functional on open subset of CDX. And after that, in 2010, Bunamor gives a generalization of Sanderson results in the case of uniformly complete Riesz spaces. And after that, by using the tensor product, theory, Busque-Zambou gives the same results in the case of Banach-Lattice by using tensor product. And after that, with a collaboration of Professor Meyer, we give the same result of Bunamor, but by a topological approach. We give the same, we generalize the same result of Sanderson in the case of uniformly complete Riesz spaces, but by easily Y by using a topological approach. And then by my in collaboration of Mukadem, we generalize the result of Sanderson in the case of Riesz spaces. And recently, it means this result is not on Riesz space, not necessarily uniformly complete Riesz spaces. And after that, we generalize the same result by using topological approach. Because here, in the case in 2015, our approach is with an additional condition of that, an additional separated condition on the codomains. And recently, we can remove this condition and we give the result in the general case of Riesz space. So this is the definition of orthosymmetrical. And the same way we can define the order-bounded techniques for the multilinear maps. So we can say that a multilinear maps is positive if Txy is positive whenever for two element positive, and with the same of the order-bounded multilinear. It's the same thing, is the same way to define the case of positive and order-bounded in the Riesz spaces. Now, for the definition of the array continuous maps, T, E, F in F here is uniformly complete Riesz spaces or Riesz spaces or topological Riesz spaces, topological vector spaces. We can say that it is array continuous if for every element X, Y converge vers 0, so their range converge also vers 0. T, X, Y, and IY converge vers 0 uniformly by the uniformly topological. We give some classical definition for these spaces. That this classical definition we can use in this talk. They said LBY means the all-order bounded operator in A. And the definition of orthomorphism is if we have Tx infimum of Y is equal to 0 for every disjoint 2 element, and the set of all orthomorphism is denoted by ort. And the definition, and the classical definition of the F algebra, whenever x infimum Y is equal to 0, then we have this condition. So the important structure of the set of all orthomorphism gives that orthomorphism is an F algebra respective to the composition as multiplication. Moreover, the identity is the unit element of orthomorphism, and in particular, the F algebra is semi-prime and commutative. So it means the multiplication in ort, we can commute the multiplication in the space of orthomorphism. And there is an important structure theorem in the case of orthomorphism that if we take, if A is an F algebra with unit element, then this mapping is Riesz and algebra isomorphism. So we can say that orthomorphism for an F algebra with unit is isomorphism to the whole space E. A dedicatory space is said to be universally complete whenever every set of pairwise disjoint positive element has a supremum. And every Archimedean space has unique universally completion denoted by E. Why we speak about E? Because there is an important structure in the universally complete, that the universally complete that E can be identified with order as Riesz subspace of the universally complete, and also that the universally complete is an F algebra with unit elements. So I start with the first important result, which is given by Benamor, and we generate this result by another by using the topological Riesz spaces, that if F be Riesz uniformly complete Riesz spaces and F a Hausdorff topological vector spaces, not necessarily Riesz spaces, because in the definition of orthosymmetric map, we cannot need that the codomain is a Riesz space, that only it may be a vector spaces. That if we take phi E in F be a continuous orthosymmetric bilinear map, then necessarily phi is symmetric. With this, generalize the classical case, for example, for almost F algebra. For almost F algebra, because it's commutative, so the product is symmetrical, and this is generalized the work of Buskes, of Sanderson, of some others. And then with a separation conditional, that if we take a continuous, not necessarily order bound, not necessarily positive, it is only the hypothesis of continuous orthosymmetrical multilinear map, with the separation condition that then the range of T is separated points, then for every permutation, we can T, XY, XY, we can permutate for every permutation in S1, for all elements in A. So as an application, an important application, we can give this result if we composite T by some orthomorphisms, that and T is only continuous orthomorphismic multilinear map, such that T with this condition of separation in the range, then we have for all orthomorphisms, we have this equality. And then in my recent works, we can also remove this condition. So it means we cannot need the separation condition. Now, what it means by homogeneous polynomials of degree n, if we take E is a vector lattice and F is topological space, there is a topological and vector structure in F. A map P, E, and F is called homogeneous polymorphs of degree n if Px that it's T, X, Y, X, where T is n multilinear map from n into F. And what means by orthogonally? What means by orthogonally additive polynomials? It means that orthogonally additive polynomials if P x plus y is equal to Px, where for every disjoint two elements, and we cannot PCY of n the set of all continuous orthogonally additive polynomials. For all continuous, not necessarily orthogonal, is the only structure because the Riemann space is not be a vector lattice, so we cannot have a structure of free spaces here. Donc we have only the topological, so the set of all continuous and homogeneous polynomials, additive polynomials from E to F. So in this talk here we study this space and give some important property in this space of polynomials. Let E be an F is Hausdorff topological vector space, not necessarily vector spaces, just vector. Excuse me, we have a problem for internet.
Oh, no problems.
We can continue?
Yes, please.
So, excuse me. So if we have an Archimedean vector lattice and F is Hausdorff topological vector space, not necessarily vector lattices, and P is a continuous orthogonally additive polynomials who associate symmetric multilinear may be satisfied that this range is period spans, then T is orthosymmetrical. With this condition, and by my recent works, we can remove this condition. It's not a problem. So a structural problem. So if we take an Archimedean vector lattice and F is Hausdorff topological vector space, now for every continuous orthogonally polynomials, we have this representation theorem that we can represent via a linear operator. So with this equality, we can linearize every continuous orthogonally polynomials. But our approach fails to non-continuous cases. It means that the condition of continuous for polynomials is very interesting to find this representation theorem for the continuous orthogonally polynomials. So this is an example for the piecewise functional polynomial functional. So it's not difficult to see that this maps is not symmetrical. So is orthogonal, but it's not symmetrical. So is orthogonally additive, but it's not orthogonally orthosymmetric maps, two orthogonally symmetric bilinear maps, but it's not symmetrical. So our approach fails in the case of non-continuous, and we can prove easily that this multilinear maps is not continuous. So by this by the last represents, we can define a new absolute value in the polynomials there is some ways to define the absolute value in the case of polynomials, but I think that it's the easy one, because we have an operator, a linear operator. So if f is digit complete, so we can define the absolute value for an order bounded So we can define the absolute value for polynomials by this way. And then we have an important structure for all the case of orthogonally order bounded polynomials, because order bounded it comes continuous. So we have this important structure that the set of all order bounded polynomials is a space. And then if f is didactic complete, so we can find this important result that the all set of all order bounded polynomials is isomorph, is lattice, and is isomorph to the set of all linear order bounded linear operator from this product, where it means the relatively uniformly complete of E. And then if we take now a polyomorphism, if we give this new definition of polyautomorphism, so we can give the same thing for linear operator to the case of polynomial. So we can say that a polynomial is said to be polyautomorphism if the associate map, the linear associate map, is a weak orthomorphism. Here is why is weak orthomorphism, because the first three spaces, the domain of TP is subspace order dense in the universally complete. So this is a weak orthomorphisms. We can say that the new definition of polyautomorphisms, and with the same thing, we can say that the P is said to be polymorphisms if the associate linear is homomorphisms. And then if we define the last absolute value of a polynomial, we can see, and we can prove easily, that if in the case of polyautomorphisms, the absolute value of K is the absolute value, is the same thing, is the absolute value of the associate multilinear maps of P. And then we have the same things for the general and the linear case, that the absolute value of Px is the absolute value of Px, and the part plus and the negative part for all x positive. And also we have a very nice extension theorem that if we have a order bounded multilinear polynomials, order bounded orthogonally polynomials, and that K is less than P, then we can extend K to the whole of E, and K is definite in the Riesz subspace of E. So it means we have the same extended theorem in the classical linear case. And then we have the all orthogonally order bounded polynomials. It's in the orthogonally order bounds in the Dedekind completion of E. This inclusion, it means that every polynomials in E, we can extend it to a polynomials order bounded orthogonally polynomials on the Dedekind complete of E. This inclusion is not inclusion in the sense that this is in the sense of extension operator. And then also every homomorphisms, polyomorphism, we can extend it also in the Dedekind complete of the E. And finally, every polyautomorphism in E, we can extend it in polyautomorphism in the Dedekind completion. Here, this the Dedekind completion of E, the notation of the Dedekind completion of E. And finally, thank you very much for your attention.
So thank you, Professor, for this nice talk. Are there any questions or comments?
Yusuf, you don't have a question?
Of course I have.
I wait you.
You said that you dropped the separation condition.
Yes.
I want to know what's the idea of the proof, because in the case of when E prime is separating, we can compose with function.
Yes. Yes. In the case of where we have the separation condition, it's the idea is to compensate with linear form linear maps, and then we get the range is R, and then we can which it's Riesz space, and we can conclude by the preceding classical theorem. But in the case when we remove the condition of separating hypotheses, we have some difficulty. But we finally by difficult techniques, by using topological techniques and the tensor product in the spaces, we can prove this by representation with functionals. It means by extension theorem. By using topological techniques for
you will work locally or?
Yes. We work locally, and then we can generate the result.
Okay, thank you.
It is a recent paper with my student Dor'i in the mathematical analysis.
Okay, I will see it.
So, any other questions?
Yes, I have a question about this slide that is projected now. Is this your results? Because I see similar ones some years ago with Professor COSAEF or COSAEF.
Yes. There is the similar result by COSAEF and Busquets. They not use this product, this value absolute. They use another technique with variational conditional in absolute. By this, the isomorphisms is depend in the absolute value. In the absolute, here is the new absolute value for the polynomial, which I think that it's natural absolute value, because it's depend in the in the associated linear operator.
But I am okay. But
the difference is
I see Zarina here, but I think that Zarina can speak also, but because I am almost sure that is the same result. Not about polymorphism.
Yes, they give us the same result here. But here, the result here is isomorphism. So it depends in the order. Here in the order, this is the order that we have. We take the absolute value of the polynomials is the absolute value of the associated linear maps. Oh. And there is another technical for there is another definition of the absolute value in the other paper.
No, but
it's okay. It's okay.
It's okay. And when F is just a topological vector space, when F is just a topological vector space, like at the beginning of the talk.
No, it's here. It's we cannot define the absolute
it's
value.
Dedekind completely space. But
yes,
at the beginning of the talk, F was
Yes. But to define, there is the important, the representation theorem for in the general case. But if we have to define the absolute value, that we need that the range is a vector space in this case.
Okay.
It's okay.
Thank you.
Thank you. Thank you very much.
Is there anyone, someone else who wants to interpret? So thank you again, Professor Chil, for this interesting talk. We have a 5 minutes break until the next talk.